Welcome to G Fun Facts Online. The red planet was not always red. Before the iron in its crust oxidized into the rust-colored dust that now coats its surface, and before the atmosphere thinned to a wisp of carbon dioxide, Mars was a world of blues and grays. It was a world of thundering rivers, silent, mirror-like lakes, and perhaps even a vast northern ocean that reflected a younger, dimmer sun. The story of water on Mars, known as Martian Paleohydrology, is not merely a geological curiosity. It is a ghost story written in stone, a narrative of a planetary death, and the most compelling treasure map in the history of human exploration. To trace the ancient water of Mars is to walk the line between a dead world and a potentially living one, investigating a history that spans over 4 billion years. To understand this history, we must first look at how our perception of Mars has evolved. The human fascination with water on Mars began long before the first rocket defied gravity. In the late 19th century, the astronomer Percival Lowell peered through his telescope in Flagstaff, Arizona, and believed he saw a network of fine lines crisscrossing the Martian globe. Inspired by the Italian astronomer Giovanni Schiaparelli, Lowell called them canali. He interpreted these as artificial irrigation canals, engineered by a dying civilization to transport water from the frozen polar caps to the arid equator. It was a romantic and terrifying vision that captivated the world. While the space age shattered Lowell's vision of a hydraulic empire when Mariner 4 flew by in 1965 revealing a cratered wasteland, the core of his obsession was prophetic. Mars was a wet world. Lowell was just billions of years too late. The channels were real, but they were not carved by Martians. They were carved by physics, time, and catastrophe. The true reconnaissance began with the Viking orbiters in the 1970s, which sent back images of features that looked unmistakably like dried riverbeds. These valley networks in the southern highlands and the massive outflow channels emptying into the northern plains suggested that liquid water was a protagonist in Martian history. To fully grasp this, one must understand the Martian calendar. Planetary geologists divide the history of Mars into 3 primary epochs, each defined by the state of water. The first is the Noachian period, spanning from 4.1 to 3.7 billion years ago. Named after Noachi's Terra, this is the oldest and most battered terrain on Mars. During this time, the solar system was experiencing the late heavy bombardment, a rain of asteroids and comets. Yet, amidst this violence, the Noachian was the golden age of Martian water. The atmosphere was dense, likely thicker than Earth's is today, providing enough pressure to keep liquid water stable on the surface. During this epoch, actual precipitation fell on the highlands. Rain collected in craters, breached their rims, and cascaded down to lower elevations, carving branching valley networks that resemble terrestrial river systems. This was a time of phyllosilicates, or clays. The interaction between water and volcanic basalt created vast deposits of iron-magnesium smectites, minerals that only form in neutral pH, long-standing water. If life ever emerged on Mars, it likely did so here, in the warm, muddy waters of the Noachian. As we move into the Hesperian period between 3.7 and 3 billion years ago, Mars began to change. The internal magnetic field, which shielded the planet from the solar wind, collapsed. The atmosphere began to bleed away into space. Volcanism spiked, spewing massive amounts of sulfur dioxide into the air. The water did not disappear immediately, but it changed character. It became acidic. Hydrological activity shifted from rain-fed rivers to catastrophic groundwater release. Massive outflow channels, such as Casey Valles and Ares Valles, date to this era. These were formed not by slow erosion but by titanic floods, likely triggered by volcanic heat melting subsurface ice, releasing water volumes greater than the Amazon River in a matter of days. The chemistry shifted from clays to sulfates, minerals like gypsum and kieserite that form in acidic evaporating brine. Mars was becoming a planetary salt pan. Finally, we arrived at the Amazonian period, stretching from 3 billion years ago to the present. This is the cold, dry, and oxidized Mars we know today. Liquid water became unstable on the surface, sublimating instantly into gas or freezing into ice. Hydrological activity became episodic and rare, perhaps a brief melt caused by a meteor impact. The water became locked away in the polar caps or buried deep underground. However, we don't just rely on timelines. We rely on chemistry. Water acts as a chemist, leaving behind a mineralogical fingerprint. By reading these minerals, scientists have reconstructed the pH, temperature, and salinity of ancient Martian waters. The widespread clay deposits found by orbiters like Mars Express and the Mars Reconnaissance Orbiter are the smoking gun of habitable water, implying a high water-to-rock ratio and a neutral pH. In contrast, the sulfates found by the Opportunity rover indicate a shift to a harsher acidic environment. One of the most famous discoveries came from Opportunity in Meridiani Planum, where it found small, spherical concretions rich in hematite, nicknamed blueberries. These formed when groundwater flowed through porous rock, dissolving iron and reprecipitating it in concentrated spheres. They are literal stones formed by flowing water, proving that vast areas of the Martian subsurface were once saturated aquifers. Another significant find was by the Spirit rover in Gusev crater, which churned up soil rich in hydrated silica, or opal. On Earth, such deposits form around hot springs or hydrothermal vents. This was the first strong evidence of a hydrothermal system on Mars, an environment where heat and water mix to provide a perfect energy source for microbial life. Before we could touch the surface to find these minerals, we had to map it. The fleet of orbiters circling Mars has provided a global view of the planet's hydrology. One of the most debated ideas is the existence of a primordial ocean covering the northern lowlands, known as Oceanus Borealis. Mars possesses a crustal dichotomy where the southern hemisphere is rugged and elevated, while the north is smooth and low. Many scientists believe the northern basin was once filled with water. Data has revealed features that look suspiciously like ancient shorelines wrapping around the northern plains, and delta formations where rivers from the highlands would have emptied into the sea. Recent analysis suggests a connected oceanic system existed as late as 3.4 billion years ago. Orbiters also revealed the valley networks, which are dendritic or tree-like branching structures that follow topography, suggesting heavy and persistent rainfall. In contrast, the outflow channels are giants lacking tributary systems, emerging full-born from chaotic terrain where the ground seemingly collapsed. The leading theory is that these were formed by the sudden release of pressurized aquifers, perhaps triggered by magma rising beneath the cryosphere. While orbiters gave us the map, rovers gave us the ground truth. The progression of rover capabilities mirrors the deepening of our understanding. The twin rovers, Spirit and Opportunity, landed in 2004, tasked with following the water. Spirit initially struggled in Gusev crater, but eventually found evidence of water alteration in the Columbia Hills. Opportunity scored a major victory in Meridiani Planum, finding the hematite blueberries and jarosite, confirming that Mars had standing bodies of acidic water. The Curiosity rover, landing in Gale crater in 2012, took the search to a new level. Gale is a massive impact basin with a central mountain, Mount Sharp, composed of layered sediments. As Curiosity climbed the mountain, it read the layers like pages in a history book. It found rounded pebbles that were too heavy to be moved by wind, tumbled smooth by a knee-deep stream flowing at a brisk pace. It found mudstones indicating that Gale crater hosted a freshwater lake for millions of years. This lake was neutral, not acidic, and contained all the chemical ingredients necessary for life. In the mid-2020s, Curiosity discovered wave ripples, proving the existence of shallow, ice-free bodies of water subject to wind, and even pure elemental sulfur crystals, pointing to a complex subsurface water system. Then came Perseverance, landing in Jezero crater, a site chosen specifically for its hydrological features. Orbital images showed a river channel breaking through the crater wall and depositing a massive fan-shaped delta. Perseverance confirmed that this delta was composed of sediments carried by a river that flowed into a standing lake. Ground-penetrating radar allowed the rover to see underground, revealing sloping layers of the delta. Perseverance found carbonates, excellent for preserving biosignatures, and fine-grained mudstones with high concentrations of organic molecules. These rocks were deposited in a low-energy lake environment, exactly the kind of quiet place where microbial life might thrive. Furthermore, Perseverance found massive boulders sitting on top of the delta, evidence that the gentle river eventually became a raging torrent of superfloods as the climate shifted. China's Zhurong rover also contributed, finding evidence of hydrated minerals in the northern plains, supporting the theory of vast ephemeral seas. But if Mars had oceans, rivers, and rain, where did it go? This is the central mystery of atmospheric evolution. The MAVEN mission provided the answer. Mars is small, and when its internal dynamo shut down, it lost its global magnetic field. Without this shield, the solar winds slammed directly into the upper atmosphere, stripping it away for billions of years. As the atmosphere thinned, the pressure dropped below the triple point of water, meaning liquid water could no longer exist. It boiled away or froze. The oceans sublimated into space, torn apart by solar radiation. However, not all water was lost to space. A significant portion went down. Data from the InSight lander suggests that the Martian crust is porous and fractured. Seismic analysis points to the possibility of liquid water existing deep within the mid-crust, 10 to 20 kilometers down. The crust acted like a sponge, soaking up the oceans as the surface became uninhabitable. Today, Mars is not dead, merely dormant. Water exists in vast quantities, just not as liquid on the surface. The polar caps contain enough water ice to cover the entire planet in an ocean 20 to 30 meters deep. Buried glaciers in the mid-latitudes contain vast reservoirs of relatively pure ice. We even see hints of active cycles, with recurring slope linea, dark streaks that appear on slopes during summer, likely caused by hydrated salts absorbing atmospheric moisture. Understanding this paleohydrology is crucial, because the mantra of astrobiology is to follow the water. Paleohydrology tells us where to look for life. Deltas like the one in Jezero are suited for preserving organic matter. Hydrothermal vents like those in Gusev offer energy-rich environments. And if life retreated as the surface died, the deep crustal aquifers might be the last refuge. Perseverance is currently collecting samples to be returned to Earth, where we can analyze the isotopic ratios of water trapped in minerals to see if biology was involved. To fully appreciate this, we must consider the physics. On Mars, the triple point of water dominates. The average surface pressure allows water to boil and freeze simultaneously. But ancient Mars had higher pressure, likely allowing rain. Furthermore, Martian water was likely a brine. Salts lower the freezing point, allowing liquid water to exist at temperatures far below zero. This means wet Mars might have actually been a sub-zero slush Mars for much of its history. We also look at isotopic evidence, specifically the ratio of deuterium to hydrogen. Lighter hydrogen escapes into space faster than heavy deuterium. By measuring the current ratio, scientists calculate that Mars started with a global equivalent water layer of at least 137 meters. Martian paleohydrology is a discipline of reconstruction. From orbital maps to microscopic clay analysis, we have pieced together a history of a world that was once startlingly Earth-like. The tracing of ancient water is more than an academic exercise. It is the roadmap for our own future. The buried glaciers and hydrated minerals will provide water for astronauts, oxygen to breathe, and hydrogen for fuel. We follow the ancient water, not just to learn where Mars has been, but to ensure that we can go there. As rovers continue to climb sedimentary mounds and orbiters pierce the crust with radar, the ghost waters of Mars become clearer. They tell us that the universe is capable of generating habitable worlds, even if it cannot always sustain them. And they whisper a tantalizing possibility, that in the deep, wet rocks, or in the frozen ancient muds, we are not alone.